Yeah, so my name is Sue-Ann, as Maddie introduced me, and today I'll talk a little bit about deep learning, kind of the state of the world a little bit, and deep learning pipelines, which is a kind of Databricks answer to the problems people face when they're doing deep learning. So kind of an overview. As I said, we'll talk a little about the current state of the world, the philosophy behind deep learning pipelines, and kind of the tools in there that help you with doing end-to-end workflow with deep learning, and a little bit about the future. So we can start with what is deep learning. Actually, how many people here have maybe like played with deep learning or no? Oh, that's good. Okay. I'm not sure about the face you made, but okay. Okay, so deep learning is just really a set of machine learning techniques that use these layers that transform numerical inputs. So it can be used for any normal machine learning task like classification, regression, or learning arbitrary function mappings, right? And it was really popular in the 80s, and back then they were called neural networks. But they came back in kind of these massive forms. And the reason they have become feasible now is thanks to the advances in being able to collect a lot of data and store them and use them using better computation techniques and hardware. And we've seen a lot of success of deep learning in fields that have to deal with complex data. Like game playing like AlphaGo with a complex state space, or working with things like images, text, and speech. But deep learning can be often challenging, and to sort of summarize, there are kind of three parts. One is that to train a single model can actually take a lot of compute resources and time. Compounded by the fact that it actually takes a lot of engineering hours to design a good network and then iterate and so on. So if you combine those two, then it could take months to actually build a great model for your task. And because these models are really complex, it can take a lot of often labeled data to do this, to train a great model, which you may not have access to depending on your circumstances. And what makes these parts worse are a set of kind of smaller problems, I guess. One is that it's actually tedious or difficult to distribute computations in a lot of these deep learning frameworks. Another is that there is no exact science around deep learning, so it takes a lot of tweaking and experimentation to get a good model. And third is there are many different frameworks out there for doing deep learning, like TensorFlow, MXNet, PyTorch, and so on. And they tend to be low-level APIs that require quite a bit of learning curve to really know how to use them. And I mentioned earlier, complex models means you need a lot of data. So these things have kind of led to limited adoption in industry of deep learning. And when you hear about kind of success of deep learning, it's usually these industrial giants like Google or Facebook or Amazon that have seen a lot of success because they have those resources, time, and data. So the question we asked was, how can we accelerate this road to better availability to everyone to do deep learning? And that's why we built deep learning pipelines. And kind of the theme we went with here is to focus on the ease of use and integration. And it's an open source Databricks library. I'll have some links for how to access it and stuff. And also without sacrificing performance while keeping the ease of use. So if we go back to this slide of the challenges we talked about, and kind of look at each item, and what we really want, right, in this world is that at least for the common workflow and tasks that are benefited by deep learning, it shouldn't be difficult to distribute these computations. It should be easy to scale. Tweaking takes a lot of time, so hopefully you don't want to do a lot of tweaking. The API should be simpler and higher level for at least common things. And we don't want to always have to have a lot of data to solve these problems, because you may have problems that are kind of new in your application. So how we address these things in deep learning pipelines is are the following. So for scaling, we use, as you might imagine, Apache Spark to scale out the computation for common tasks. For requiring little tweaking, we try to leverage as many well-known model architectures for the specific problems as possible. And then to make it easier to write, we integrated with MLlib Pipelines API and using the pipeline concepts we'll talk about a little bit later. To kind of capture these workflows with very few lines of code. And finally, we can leverage, there are lots of pre-trained models for specific tasks out there for deep learning, and we can leverage them and essentially tweak the model a little bit. We'll see examples of this to get great models with little data. So I will actually kind of, to demonstrate these points, I'm going to do a little demo where I need this. Sorry. Yeah. I need to type a little. So okay. And we're going to build a like visual recommendation AI, fancy animation. And actually, this recommendation AI takes 10 minutes to train. And it's going to use 7 lines of code in Spark. And it's actually going to require 0 labels, and we'll see how that happens. And the particular recommendation task we're going to deal with today is like visual recommendation of shoes. So given a particular pair of shoes, we're going to find shoes that are similar visually, partly because I like shoes, and this is a real actual task that is used in the world, right? Okay, so let's see how we can do this. All right. Oh, sorry. I can't see the notebook. Let's see if this works. Okay. Should I mirror? Should I just go mirror? Yeah. Sorry. It is mirrored. Oh, okay. Now that I'm out of like presentation mode, I can actually see it. Okay, so in this notebook, I've loaded a data set of shoes. There are 34,000 of them. They come from a website with a lot of shoes. I actually used Spark to scrape the data, which was fun. It's a separate story. Okay, so we can look at the shoes in there. And there's a pretty good variety of shoes, from like heels to athletic running shoes, tall boots, sandals, and so on. So now, as a data scientist, given a pair of shoes, I want to find other shoes that are similar, right? So how would I go about doing that? One natural algorithm to consider is nearest neighbor. So for those who are maybe not as familiar, nearest neighbor works by assuming that your data points live in a reasonable representation space, such that things that are closer in that space are more similar than things that are further away. So this actually requires no labels. That's how we got away with 0 labels. But you do need a good representation of the data points such that like this close means similar is true, right? And that's going to be key to our success today. So let's look at what we have here. So I've also loaded here kind of this like vector representation of the images, which is just a vector. 255 is for all the white space around the shoes. And then one important thing is that actually these shoes live in these 500,000 dimensional spaces, which is pretty large. And one consequence of that is going to be, comparisons might be a little expensive between the points. And what's worse is, given a pair of shoes, you have to look at all the 34,000 shoes in your data set to find, let's say, top 10 most similar things. And that can be very expensive. Luckily, MLlib has an approximate nearest neighbor algorithm called locality-sensitive hashing, or LSH. And that essentially finds kind of these approximate neighborhoods for each data point, so that you only have to search in that neighborhood to find your top K similar shoes in this case, instead of the entire data set. So that's pretty simple to write here. And actually, let me start running this. And here we've written kind of like a small helper function to do this. We're going to use an LSH algorithm called bucketed random projection LSH, which just helps you compute Euclidean distances quickly between things. Here we just make the object, call fit, and we just need to call approx nearest neighbors on this with the set of candidates, which will be all the shoes. The key, which is this array representation of the images, and we'll find the top 10 closest shoes. And here, what we're running this on is actually, we haven't done any deep learning. We're just trying it on raw images to see how reasonable that is. It seems like it could be reasonable because the picture has all of the data you need visually, right? So here is the result from that. The top image here is the original shoe I was looking at. And these are the results, and they're not horrible. They're kind of like same color-ish. Like we didn't get any boots, so that's good. But I started with these like summer sandals and got winter slippers, and that's probably not actually productionizable yet, right? So what are we gonna do? Obviously, we're gonna use deep learning. So, okay. All right. So I'll actually explain exactly what's going on with this deep learning section a little bit later in the slides. But essentially what we're going to do is we're going to use deep learning to change the representation of the shoes from the raw space to something that's going to be more reasonable that the deep learning models can capture. So to do that, this is from Deep Learning Pipelines. It provides a tool called Deep Image Featurizer that takes the image and then outputs some higher representation of that image that's going to contain more useful things like edges and texture and so on. So we can have this featurizer featurize the image data. I'm not going to run this here because this is the thing that takes 10 minutes, and that 10 minutes to do it. But we're going to now run the exact same LSH algorithm to find the nearest neighbors on this, higher represent deep learning features. Okay, so here's the result. This looks much better, right? Now we actually have other sandals, and not only are they kind of the same shape, we can actually see that it finds shoes that are a little bit maybe differently shaped, but have the same stylistic details like this crochet, and they're kind of similarly heeled sandals and so on. So that was cool. Yeah. That's funny. Okay. I actually have no idea how much time I have, but I'll just. Okay. Well, okay. So here are some other examples from like that sample data set we had in the beginning. It's really pretty good. Yeah. And I actually did like no selection of shoes at all. I just like picked random ones, and they were this good. Okay. So that was cool. So now I'm going to talk a little bit about kind of the different parts of deep learning pipelines, a little bit more about what actually happened there, and so on. And to do that, it's useful to look at sort of the typical deep learning workflow, which is really, really similar to typical machine learning workflow. So first, you'll load the data, but in deep learning, a lot of the times it will be more complex data, like images and text or time series. And then, as usual, you might do some interactive work to figure out, what's in this data set, what's going on. And then you probably want to start, trying to train some models. For deep learning, usually you have to choose an architecture or create one, and then optimize the weights in the neural network. And then you'll probably evaluate the results and then potentially retrain based on what you see and how much you like it, right? And then finally apply the model to some unseen data that you want to actually use it on. So we have these steps. And in deep learning pipelines, we kind of have some tools for each of these steps that we can talk about. Currently, the library focuses a lot on images. And it's kind of, I think of it as like showcasing one vertical with some of the tools that can be used that can be generalized to others, and I'll talk about that a little later. So for example, for images, it provides image loading functionality in Spark, which Spark is missing. And then for interactive work, it has kind of built-in ways to apply pre-trained models for images, for example. And then for training, it has tools for transfer learning and distributed tuning. For applying the models, it has kind of easy ways to apply the models in batch using Spark, or deploy the models in SQL. So today I'll talk about kind of these parts. The other parts, we did have a deep dive session at the last Spark Summit Europe. So if you're interested, you can look at that, and that kind of talks about everything more in detail. And I'll have the link at the end. Okay, so let's talk about these steps a little bit more in detail. So loading data, as I mentioned, it has support for images in Spark and dealing with loading and dealing with images. It's just a simple function where you can just say read images with the directory that contains the images, and you'll get out a data frame that has the image data in it. And what it provides is image schema, which is a way to represent these images in Spark directly, as well as this reader and kind of conversion functions from to and from NumPy, so you can kind of work with Python libraries as well in between if you need. And again, kind of the most of the tools we'll describe in the later steps of the workflow will be on these images mostly. And I think this is good news, which is like the image support will actually go into Spark 2.3 from this library. So that should be kind of native to Spark from then. And this is joint work with Microsoft. Okay, so now that you've loaded this data, what can you do? You can do some interactive work, which can be in the form of kind of applying popular models. And essentially what this does is it makes some of these popular pre-trained models accessible through MLlib Transformers. If you're not familiar with MLlib Transformers, it's just a thing that applies some function to the data, and we'll see more of that later. And here, all you have to do is call this, make this object called the Deep Image Predictor, and then apply this and specify. I don't have the pointer. Okay. Specifying a model name. There's kind of a set of nice models, especially for image classification, and then just call that on the image data frame that you got from just loading that, right? And what this will return would be, like, for example, a set of labels for things that could be in this image. So this might be kind of a nice way to explore your data set, or if you happen to actually have a problem, for example, classifying ants versus bees versus ladybug that's in this pre-trained network, you could just use it right away. Okay, so next I'll talk about training and transfer learning. So what we just saw was just applying pre-trained models that are out there, those developed by the community of like researchers and engineers working on deep learning. And that could be applicable to your data set, but in most cases, that's probably not true, right? You probably want to classify shoes or some other thing. So in that case, training from scratch, as we talked about before, requires a lot of data, a lot of time, a lot of engineering hours and resources. And I think one of the really powerful ideas in deep learning is transfer learning, which comes from the idea that intermediate representations that are learned in deep learning for one task can be useful for other related tasks. So briefly, here is how transfer learning works. Here's a representation of a neural network. Let's say it's trying to do image classification that classifies things like pandas and raccoons and cars and other things, right? And the truth is there are, a lot of great models out there for this particular task. That have been trained on millions of models, over months and years and decades of research. And the really powerful part about this is that the models have gotten so good that the intermediate layers in the model have come to actually represent kind of higher concepts about the image. That might be, edges or textures, or even kind of whole objects in the later layers of the model. So what we can do is kind of get rid of the layer that tells you what the labels are, take instead one of these intermediate layers that have a really good representation of the image data, and then if you have a new task, stick on probably a much simpler classifier on top of it, using the output of the network as the new set of features, and then train on your maybe new data set. For example, here you might be like flower classification, which is more specific than what the model was originally trained to do. Right. So, for example, you might represent something like this. Well, in deep learning pipelines, it's represented as this MLlib pipeline. Actually, that may not make much sense if you don't know MLlib. We don't have time for it. So, but essentially, all you have to do then is create a featureizer, which featureizes the image, again, using a model of your choice. There are other models than Inception v3 in this library, but we like it. And then you just stick on a classifier like logistic regression after, put it in a pipeline, which is another MLlib concept, and then train it. So now you can train a new image classifier for your task in just 4 lines of code, which is pretty powerful. Okay, so transfer learning kind of in its normal definition tends to be for classification tasks, for things that are maybe like similar tasks like image classification, but in a new domain. But I think of kind of other forms of leveraging these learned representations as transfer learning as well. And that's sort of the shoe example we saw earlier, where we took that representation that was learned in deep learning and then used not just, classification at the end of it, but you can use, other similarity-based machine learning algorithms like clustering or distance computation. And this kind of lets you do other things like duplicate detection or anomaly detection, use it for recommendation, or search result diversification kind of things. So there are wider, I think, applications of that. Okay, so as I was saying, we'll skip hyperparameter tuning evaluation. And as kind of the last set of tools I want to talk about now, after you have a model, how do you apply that model to your data? And we'll focus here mostly on batch prediction. So batch prediction, which is just, offline you have a very large data set and you have this deep learning model. How do you apply it efficiently, right? And Spark should be really good at this, right? This is a very embarrassingly parallel task where you just apply this thing to the data in a distributed manner or parallel. And one, I think, useful concept to finally actually know in MLlib is that a model is a transformer in MLlib. And a transformer is really just, it takes a data frame and then it outputs a data frame with another column attached to it. So it looks something like this, where you create a transformer object, you tell it kind of which columns you're gonna apply whatever is happening inside to. You tell it what, okay, it does work. Okay, you tell it where to put the result of that computation of applying whatever it is to the input column. And then in this case, we might have a transformer that takes a model specification, like what is this deep learning model? And then again, you can just apply that to some data frame that contains this input column in there, and then you should get the output in this output column, right? So I think that's a simple enough concept. So I think what is interesting about this kind of batch prediction and model application in deep learning pipelines is that there's sort of a hierarchy of these transformers in deep learning pipelines that all take as input the image and then output some vector output. Okay, it will become more clear why it's interesting, hopefully soon. So actually, these deep image predictor and featurizer that we talked about earlier that gave you kind of these pre-canned answers or the featurization mechanism are also just these transformers that take in an input image, then output a vector that was either the label probabilities or the features, right? Internally, they're actually represented, or they call another transformer that is weirdly named image transformer because it just takes a model name and then it's going to instantiate the model inside. So these things just call that with a model name. And then underneath that, it's actually powered by some other transformers that are closer and closer to the deep learning frameworks that are actually used underneath, like Keras or TensorFlow, right? So I think the reason I think this is interesting is because it kind of exposes these tools at different levels of abstraction. You can kind of go from not knowing anything about deep learning and just applying these models at the top level, all the way to the bottom where you're probably training your own models and then feeding that into these transformers to apply that. Am I severely over time? Okay. Okay. And this is just for images, but we're actually kind of trying to build similar things in other domains like text, where you might see kind of the same kind of pattern that is ultimately all backed by kind of the same backend underneath. And some of these things are actually being built in right now, and you can check them out. Okay. Is the animation working? Okay. Yeah. And again, kind of these levels, I think, represent one of the philosophies that deep learning pipelines tries to address, which is that these common tasks should be easy, using pre-built solutions or things that are 80% there for things like transfer learning, and the advanced tasks where you need to do more modeling should also be possible. For example, by being able to distribute it easily using Spark. So I think I already talked about some of these in progress things for text and so on. So then you can imagine sort of the direction of the deep learning pipelines where we can apply this sort of philosophy for easier, common things should be easy, advanced things should be possible. So we're considering things like non-image data domains like video, text, speech, and so on. We are working on some distributed training things to make that advanced part more possible, and also considering kind of support for backends that are not just TensorFlow, but MXNet, PyTorch, and so on. And if you have any feedback about kind of which directions, I'd love to hear them. Yeah, actually that's it. Yeah. Okay. There are a bunch of links. I think this slide. Yeah. Any questions? Yeah.
I had a question. So I saw that you did your deep learning, and then you went to a logistic regression.
Yeah.
For features and then logistic regression.
Mm-hmm.
Some cases people will do feature extraction from different types of
Yeah, so in this particular case, right, like that we put, for example, logistic regression, but you could really put anything there that could do classification. So potentially using deep learning, again, could give you a more powerful classifier. I think in a lot of these cases where the base model is really, really good at representing that space, you don't necessarily need a more complex model like deep learning afterwards. But, you know, something you could try. Yeah. Person, I think.
Hey, I was curious, like, what is the roadmap on the tech side for deep learning? So I saw like you showed like something for embedding, but what about like RNN, LSTM?
Yeah. We don't have anything kind of in the works right now. Definitely, right, like those are kind of common models that would be nicer to have like better either training or using them. There's some embedding PRs out there. You can actually check them out that are currently being worked on. Yeah, I think we could discuss it a little more if you have, you know, some ideas around that. Yeah. Yeah. The question was, would applying something like PCA before applying the deep learning model help? I guess it kind of depends on your domain. I think like the general philosophy around deep learning is really to try to help you so you don't have to do things like, you know, dimensional reduction like that beforehand, right? Like it should kind of try to handle it for you. You know, ideally the architecture is good enough that it can kind of do those kinds of dimensional reduction things inside. Yeah. Any other questions? Anyone?
All right.
Okay.
Thank you so much.
All right.
Well, let's give a final round of applause to all our speakers here tonight. They are, you know, they have amazing accomplishments and even significant contributions to technology, computer science, diversity, and of course Apache Spark. So thank you so much. And thank you all of you for sharing your evening with us. Thank you. We hope to see you at future events. So please come back.